Okay, everyone, welcome to CS235, Applied Robot Design for Non-Robot Designers. This is lecture 17. Yes, lecture 17. Today we're going to be talking about linear motion. We have a ton to get through. We may or may not actually get through all of it. As such, unless it's a really pressing question, we may hold it to the end. So feel free to ask if it's burning a hole in your brain. And any questions about the final project we'll talk about after. I know some of you are planning to, on staying and talking to me anyway. And then at the end of the lecture I have some stuff to hand out. So it would behoove at least one person per team to stick around an extra 5 minutes to get your handy dandy objects. So I'm just going to jump right in. So we've talked a whole lot about revolute motion, rotary motion, and how to constrain it, how to do transmissions, etc., etc. And one of the things that you're learning from the final project is that real-world problems often require linear solutions. It doesn't mean that you couldn't build your chess-playing robot with all revolute joints. Of course you could, and I've talked to some of you about doing that. But it can make things a lot easier to have a prismatic joint. So this is the kinematic symbol for it. Okay, and so this sort of makes sense. This is like a slide, and this is a head that moves up and down along it. And this is called a P joint, or a prismatic joint, or linear. And so if you had an RRP robot, what would that be? Revolute prismatic. So the first thing you need to know, and this is a common misunderstanding, is there are two parts about prismatic motion. One is constraining the motion, that is making it move in a line. And then the second is powering the motion. Okay? Now this should not come as any surprise. The fact that, well, let's think about it. Have any of your labs been motorized thus far? No. And yet all of their motions have been constrained. And then for the final project we'll put motors on them, so then we're powering it. For some reason though, I think primarily because of screws, people get extremely confused about, well, are screws for constraining the motion or powering or both? So we're going to clear that up today. First we're going to talk about how do we constrain the motion, how do we get something to move in a straight line, and second we're going to talk about how do you actually force it along that line, how do we power the motion. So let's take sort of the most traditional approach, and I'm going to display it up here. So this is the Silver Falcon done by Ken and Akil Madani at MIT, and can everyone see this okay? Okay, you see these two silver shafts here? Well, that one's not silver. See these two silver shafts? 1 and 2? Is that showing up okay? Yeah. Okay, it's 1 and 2. So basically this thing just moves along these two shafts. See that? And these black things right here are little linear bushings. So let's get a hum of approval if everyone sees how this moves in terms of two rods. Hum of approval, anyone? Okay, good. I'm going to harness that as alternative energy one day. It's a field of people humming. So that's the most basic type of linear constraint, which is you have two circular rods. Okay, and then you have some type of plate with two holes in it. We fit it on here and it slides back and forth. Will this work with one rod? No. So imagine if I take this rod away and I put it on here. It's just going to rotate about this rod, right? Everyone see that? So that's why when you're doing sort of the parallel rods method for linear motion, you always need two. It's very important. Okay, so this is the most basic thing. And you could literally, one of the things they do for the Varian machine shop machining training is you basically build something like this. And all it is a block of aluminum with two holes. Then there's another block down here that holds the pins, and then two pins that this moves along, okay? It could literally be just unlined aluminum on a steel shaft. What are the problems here? Parallelism is the biggest one. So imagine we're looking at the top view. This will be just fine. But now what if this shaft is like that? It's going to bind, right? Parallelism between two rods or slides or whatever have you is one of the biggest issues for parallel motion, for linear motion, to the point that a lot of researchers and a lot of companies have traditionally avoided linear systems just because of this parallel issue. Now, one of the other issues for just this plane system is if this is aluminum on steel, it's going to be pretty high friction, right? Okay, so it's high friction because it's a sliding contact. So what could we do to minimize that? Could put a bushing in it. Okay, so now maybe we'll take something that has a flange on it. Okay, and then we'll stuff that into the hole and say this will be made out of Freelon or Teflon. These are both very low friction materials. So now it's the same block. Instead of aluminum, now it's Freelon or Teflon. So it's low friction, but still it's a sliding joint, which means we're going to have play, right? We don't have preloaded ball bearings. There has to be some clearance between the shaft and the hole for it to be able to move, so we have play, we have wiggle. We have wiggle, if this is the plate, we have wiggle like this against the extremes of the shafts, and we have wiggle like this. So, the next way up from this, in terms of niceness, would be what? What's an analog? So in Revolut, we went from just sort of a hole and a shaft that revolves. It was a plain bearing or sleeve bearing, and we went to ball bearings, and we used the balls for lower friction and less play. So we would like a ball bearing version of this, right? So that's what we have here. Everyone get real quiet, and let's see if you can hear it. Hear that? It's a very high frequency noise. Do you know what the high frequency component is from? There are balls in here, and every time the ball gets to the end of its limit and travels to the other side, it makes a little click. And so if you have balls going really fast, it goes click, 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 and then you get that noise. So these are bushings that have balls in them, and to make sure that that is very apparent, I'm going to play a little movie for you. Linear bearings. Okay. Sorry, it's a really cheesy movie. Okay. And I think he's an Aussie.
This method provides an extremely low friction mechanism while maintaining high tolerance, maintain constant pressure on the bearing surface.
Okay, now this is a different slide, so don't get me wrong, and we'll talk about this in a second. But I couldn't find any movies of the plate of the bushing, so it's the same idea though. So watch for a sec.
Bearings use 4 rows of
So see the balls in here? Those balls sit in between the. Okay, see how they're moving? So in here, or where the balls are, and then they go by in a line and they recirculate. That's why it's called recirculating ball bearing, because the balls go in a circle. So let me play that again for you.
While maintaining high tolerances and maintain constant.
Okay, so the balls are in there, and it's the exact same thing, just a slightly different geometry. So let's pause this. So this would be your shaft, and this would be the linear bushing. So as we move the shaft, the balls move with it and just go in a circle. Now is this sliding motion? No? What is it? It's rolling motion. So much lower friction, and also we can preload the balls in there so that we have much smaller clearances than we do for the sleeve bearing. So then we have much less play. So you start out, for linear motion, we'll do 2 lines. We could do plain bearings, but let's do a nicer version, and we'll do the ball bearing. Now that clicking noise, when the ball comes up here, when it leaves this and comes up here, I believe is typically when it makes that clicking noise. So that's why you get click, 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 click as each one recirculates. That's one of the downsides of these things, is I'll give you a hint. If you're making a haptic device that uses one of these, it feels much more friction-y simply because of the sound. If you hear if you hear a sound that sounds like friction while you're using a device, it's the psychosomatic thing where you feel more friction. Anyway. Okay. Okay, now these are actually really difficult to machine properly in terms of getting the parallelism right. So instead, there's a way of doing only one rod, which is called a spline. Now, where else recently have you guys heard the word spline? Okay, so let's draw what the servo spline looks like. Can everyone see over here? So the servo spline looks something like this. And I'm going to get sloppier and sloppier as we go around. Okay. And remember, we laser cut something that fits perfectly on top of this. Now imagine this is my nut. This is a laser cut nut. And then I put this on a really long servo spline. I should be able to move this back and forth in a straight line, right? Assume I have some clearance. Is it going to rotate? No, it's not going to rotate. So what this is called a spline, and this is where the servo spine gets its name from. This is basically, this isn't a technical term, this is a me term. This is sort of trapped, as in we can't move it off of here, we can't rotate. Remember, the reason we needed 2 poles for the circular shafts is because we want to get rid of the rotation. So in this case, we can't rotate and we only need one thing. So let me show you what that looks like. Okay, can you guys see that? See the sort of teeth on here? This is a spline and this is the nut, and I can move it up and down. See that? So I only have one pole and I'm able to go up and down, and watch this, I can't rotate. But what do you see? There's a tiny bit of rotation. What's that? That's backlash. So remember, this is a sliding joint, and so we have backlash in it. So if you can get away with a little bit of rotation, then a spline might be fine for you. But if you really need to get rid of rotation, you need to do something else. And typically you buy a bar of spline and then cut it to the length you need, and then they sell the accompanying nuts for it. Okay, now let's do something slightly different. We can generalize this concept. All this is saying is that this is trapped. So let's look at a couple different very common geometries and show it doesn't really matter . Okay, so say I have a rail like this, and then I have something that rides on top of it that looks like this. Will this give me linear motion? Yeah, this would be great. So this would be like a plane type thing, and I'm exaggerating this gap so you can see it. Is this going to come off? It's going to come off. I can just pull it right off. So this would be bad. Okay? Now instead, I could do this. Will this give me linear motion? Yes? Is this going to come off? No. Because see how it's sort of V'd in here? This is called a dovetail. You see this everywhere, not just in robotics. If you were to open up a nice pair of cabinets, you'll see something called a dovetail, which is basically, this is how they fit pieces of wood together. So let me show you what that looks like. The reason I'm showing you the dovetail is it's a very common shape. And then, now, see this gap? What's that going to give us? Backlash, play, wiggle. So what they often do is they'll take some material and fill this gap. Okay? What do you think would make a good material to fill this gap? How about Teflon? And then there's another one called Freelon, I believe. Teflon or Freelon. So often with a dovetail, they'll fill this gap with Freelon, Teflon. And there are two reasons they do this. One is it's lower friction. And what's the other? Reduces wiggle. Now, would this be okay? Say we came up with a super low friction metal, and we were to fill this with that super low friction metal. Would that be a good idea? No. Why not?
You want to compress a little just in case.
You want to compress a little bit without huge loads. So the reason why we're using a plastic is because it has low friction, but also it's soft enough and springy enough that we can press fit it in here, but not increase the friction so much that it's going to bind up on us. So remember, this is a plain bearing, so we don't want too high friction and we're not going to be able to move. So let me show you what this looks like. And actually, Rob, could you please help me for a sec? Just train the camera on the index title.
While you're doing that, how do you avoid that friction on the spline?
You don't, well, they have special coatings that you can get. So rather than just like a steel spline, they'll coat it with something of high lubricity. But if you really want to get rid of friction, I wouldn't use a spline. Toggle off and toggle back on. Okay, so this is a handy dandy. I ordered this from McMaster a couple years ago. And let's flip it over. So can everyone sort of see that profile? See in here? That's a dovetail. It's kind of hard to see. Do you see? Yeah, zoom in there. Do you see how it kind of curls around? That's the dovetail part. All right, zoom back out. Seriously, can everyone see this? Get the groove. See that groove? That groove is where the material fits in. There, see it? So that's what keeps it from popping off. All right, zoom out. And I'm going to try not to jam my fingers. Oh, God. Okay. Now, I don't know if you'll be able to see this or not. Can you zoom in? I feel it. Can you guys see that? All right, listen carefully. I can hear it, but the AC is pretty high. Well, over here, Rob, can you attest that you can hear that?
A little bit.
A little bit. That noise is play, but it's pretty good because, feel free to come after class. This is, I believe, Freelon lined, so they've minimized the backlash of this. Okay, you can give me 1 sec. And now, just because I know I'm going to get a bunch of questions, another lecture about this, let's generalize it even more. Maybe we're not a spline, maybe we're not a dovetail, let's just do some random shapes. So you can do plenty of random shapes. The rule is, as long as the nut shape fits the shaft shape, and there's some type of teeth that keeps it from coming off and keeps it from rotating, then we're good. So remember I told you about the micro racks? It's the really itty bitty 80-20. So they have two things. So this is a little linear system. This is basically small 80-20. And what they've done here is sort of the shape of the micro racks is this. And what they're doing is they're basically putting rollers in here. See? So you can't rotate this, and it's pressed together, so it works just fine. Rob, can you zoom in on this? So you can see this is an arbitrary shape. As long as we have rolling motion, we can't rotate, and we're trapped so we can't get off, then this is a suitable prismatic joint. Now let's talk about a few terms that will tell you why this is not a suitable prismatic joint in my mind. Remember we talked about needing two lines? And I said we need these two to be perfectly parallel? Okay. Well, what if I do this? In my mind, these are two curves that are basically parallel. But will a linear system work on this? And don't give me the roller coaster argument. We're not talking about roller coasters. We're talking about different mechanisms. Will these linear bushings work on here? No. Even though these two curves are parallel, the actual straightness of each individual rod matters. Okay? And so when you buy a rod from either McMaster or Misumi, they'll spec the straightness of that rod. Usually it'll be something like microns per meter. So if I go for 1 meter, how many millimeters deflection in any direction will I get? And so that's why when you buy shafts, there are rotary shafts, linear shafts, and then just plain chunks of metal. Plain chunks of metal typically don't do well as linear shafts. The reason you get linear shafts is because they're particularly straight. And straightness matters when you're talking about this. So now let's go back to this system. Do you think that 80-20 is particularly straight material? No. Things don't come out straight automatically. Like they do a lot of extra machining to make them straight. So if you get a random aluminum extrusion, the odds are it's actually going to be quite bent. And so at some point, either it's going to be too loose and you're going to have wobble, or it's going to be too tight and you're going to seize up. If you want to guarantee motion, which would you want? Too tight or too loose? Too loose. Okay. And then of course we have my favorite, because I made it, sort of this, which is you can take a random shape here and you can make your own random shape, as in I'm not going to make my own spline and I'm not going to make my own aluminum extrusion, but I can take a rod of aluminum and put one flat on it, and suddenly it makes quite a nice linear slide, even though it's not straight. So imagine I were to take a straight shaft from Misumi, it was a linear shaft, and then put a flat on it, then this would work just fine. So I showed you this in the last lecture. So just to show you real quick again, we have 4 bearings that support the bottom, and then these flat bearings and this flat on the shaft keep it from rotating. So I can't rotate very much, but it's very low friction. Okay, now all of these are sort of, they're not my favorites. So I'm going to show you my favorite, which is back on that YouTube thingamajigger. These are called linear guides. And sometimes they're called linear guides, parentheses, reciprocating ball bearings.
Some machines use simple rollers.
And they look exactly like this. This is a pretty good rendering. So you can go back and forth. And then in a second, so it's got the balls inside, so it's extremely low friction. Very, very little wiggle. And you can see the balls going back and forth. So let me draw what these actually look like in practice. So everybody got all this stuff? Can I erase it? Okay. So I've been recommending to some of you to do this for projects. So when you look, there's the rail, and then there's the head. So the rail has sort of a rectangle cross section, except it's got these little divots taken out of it. What are the divots for? Sure, so the divots keep it from rotating, but what else? And keeping it in place? The balls. So this is where the balls fit in. Okay, and then okay, so this is the rail, this is the head. And if we were to look from a top view, we'd see the rail and we'd see the head. Now typically the way this works is you'll have bolt holes at regular intervals on the rail. And you can get these either through holes or tapped. Now if they're through holes, we need an additional thing. I'm going to draw this. This is a through hole, and I want to mount it right here. What have I just drawn here? What's this shape? It's the counter bore for the head of the screw. You can't bolt these things down by having a screw above the rail. It has to be below the rail so the linear head can pass over. Okay? So if they're tapped, it'll just be tapped all the way through, and if it's for through hole, they'll have room for the screw head. And then here, what are these? On the head. Those are mounting holes on the head. Just a quick word of advice. When you buy these, they don't typically give you that many threads. So be careful. If you get a really small slide, you may only have like 2 threads of engagement. In terms of if I go in here, and this is my screw, I'll get like 2 threads and that's it. It's really easy to strip these out for small slides, so be careful. Okay, anyone remember? So cool, this is a perfect line of motion, basically. How do I mount it in my robot so I know where my line is? Anyone remember from previous lectures? I'll give you a hint. It involves shiny things. Dowel pins, yes. So let me use a different color. So I'm going to put a dowel pin right here and a dowel pin right here. Okay? Typically no one cares about the axial location of this rail. If they did, they'd give you some way, like they just chop these with a saw basically at the ends and then chamfer it. So you're not going to get precision location this way, but you do want precision in terms of what angle it's at, right? Okay. Now these dowel pins can either limit the motion, which sometimes is desirable, or what? You have to have some clearance here between the head and the dowel pin, otherwise bad things happen. Okay, let's talk about this. Say these dowel pins are beneath the head, and I just ram it this way. What's going to happen? Something obvious. It's going to fly off. Now, given what you just saw in this animation, what do you think is going to happen when it flies off? The balls are going to go everywhere. So I'm hoping I can actually show you this. Well, I'm not going to make the balls go everywhere, but I'm going to show you how one might consider them to go everywhere. Okay. Now they make gigantic versions of this. So I'm just giving you two sizes right now. This is the smallest that McMaster sells. Very tiny. You can see it's like way smaller than my pinky. And then this is much beefier. And so let's see if I can zoom in here. See those balls in there? See those? The little silver things? Do you see any gaps in between them? You're not supposed to have that big of gaps in here. So I lost a ball. And one might ask, hey Ruben, why is this head in your hands instead of, I don't know, on the rail? That would be a very apt question. Typically you're not supposed to take these things off. If you find these in nature without their rail, that's very unusual. So let me show you. Ella, can you please tape for me, please? You get to film the destruction. I don't know. We may get lucky. We may get unlucky. Okay. So I'm going to insert this on. Now half the time, literally, that I've done this, the balls go flying. So if any of you buy these, don't take them apart. That's very bad. Okay, so see how I'm kind of wiggling it in? Now I'm getting extremely lucky that none of them have gone flying yet. There you go. Now let's look at this. This is the cross section. Okay, and you see this moving up and down. And so in here we have countersunk holes for the screws. We have tapped threads here. Okay, now generally these things you can't locate off of either side. So I could put my dowel pins like this, or I could put them underneath. But I just told you you can't do that. How do you think you're able to disambiguate the two? Typically, they'll mill a little notch into the side that's for location. See that extra notch right here? That extra notch means you may locate on this side precisely, but not the other. And then typically they will give you an extra notch on the head too. Yeah, see on this head, can you see that there are 2 notches? And on this one there's only 1. So the one with 2 notches is the reference plane. So I can locate off of here. This is guaranteed to be extremely parallel to the reference plane of the rail. And you can see I've already assembled it backwards because this should be on this side. Yet another reason to not take these things apart. Okay, thank you. So let's talk a little further about this. So I told you how to locate here, and then I'm just going to put a little dash mark here so you can see that's the reference side. And then I'll put a little dash mark over here to show you this is the reference side. Because when I bolt something on here, say my gripper, I want to make sure my gripper is straight too, right? So some part of my gripper is going to have dowel pins. Guess I should use the same colors. Some part of my gripper, or whatever holds my gripper, is going to have dowel pins that locate against this side too. Okay? Everybody got that? Now for the rail, it doesn't really matter in terms of location. Well, actually, let's get to okay, so you saw the balls, and you saw me barely get lucky by not spilling them everywhere, but you saw on previous attempts I did get unlucky, and that's why we have gaps. Once you're missing one ball, it feels like crap. You should just throw out the slide. It feels like ka-clunk, 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 ka-clunk. You can feel it after class if you want. So don't take them apart. And I'll tell you a few other reasons why. So say I get this from Masumi, and it comes super nicely bubble wrapped, which it does, so it doesn't come apart. And then you take it and you're going to plug it into your robot. What do I need to plug this into my robot so I don't lose all the balls? I know you know because I saw it in your design.
Is it?
Yeah.
You need the stops so the carriage doesn't fall off.
You need stops so the carriage doesn't fall off. So let's put a big stop here and a big stop here. It doesn't matter what it is. I've used screw heads, I've used rubber things, I've used O-rings. I don't really care what it is. Just put something here as an in stop so it doesn't come off. And when you store these, you want to store them with something on the rail. Don't use tape. Tape leaves adhesive, gets in the balls, and it's ruined. You probably want to use like an O-ring. Rubber bands tend to melt in sort of random, non-deterministic ways, so use an O-ring. Yep?
Can't we just raise those dowel pins?
Yeah, you can do that too. But your dowel pins aren't here when you first get it out of the package. So when you buy this from Masumi and you take it out of the package, the first thing you want to do is put something on the ends so it doesn't fly off. Now Masumi is nice. They actually put these special little clips for you. McMaster is not. So I took this one out right before lecture and it almost flew off because McMaster didn't have any in stops. So the first thing you got to do is put in stops. Okay. Cool. Now let's talk about preloading. And the other reason why you can't take these apart. When you buy these things, I'll just give you the heads up. McMaster sells these. They're about the same price as Masumi, and you know none of the specifications about it. I mean, they'll tell you like moment capacity, and that's about it. Then you call them, and they refuse to tell you their vendor. So I wouldn't order from them unless you're in a pinch because you don't really know what you're getting. Masumi is excellent at these. They have the best I've found for a variety of reasons. So let's take a look at some of those reasons. Let's take a look at this. Alright, so this is one of my favorite slides. The part stub for this is SELBNL. A heads up, these things take forever to get here, so you have to order ahead. And let's zoom in on something cool. Whereas McMaster doesn't tell you crap about this, Masumi has a wealth of information. So the first thing is it shows the reference side here. Okay, so this is what you'll put your dowel pins on. Then the next thing I want you to see is this radial clearance. and it's called a light preload -3 to 0. That means when they are putting this together, is there any gap between the balls and the other stuff? 0 means it might just perfectly fit with 0 gap. What do you think the -3 microns means? That means we've compressed the entire thing together and forced the balls in so that it takes out any possibility of gap. We've preloaded the linear bearing. If it was a +3, what would that mean? It would mean we'd have up to +3 microns of play. So, and you can get these in light preloads, medium preloads, and heavy preloads. The heavier ones are for like really gigantic robots. But this is pretty nice. A light preload means we're guaranteed 0 wiggle in our linear bearing. But what does this mean? If they had to force the balls in there, can we take it apart? No. This is not preloaded. Maybe you'll get lucky and get it back on without the balls coming out. You will not get lucky with Misumi, guaranteed. If they do this, they have some special way, I'm sure, of doing it. If you take them out, it's done. They don't come unassembled. They come assembled, and if you take it off, it's ruined. Let's look at a couple other things. Height tolerance, width tolerance. This is basically talking about, how good are these dimensions. Those are important. And then let's look at something else. See these moment diagrams right here? This is showing the directions that we can apply torques and what the loads are. So say we have one that's 13 millimeters high. This tells you the number of Newton meters that we can twist before it breaks. So this one is twisting it this way, twisting in this configuration, twisting in this configuration. Typically linear slides die due to torque, not due to forces. So if you had a robot that was only going to, say it was only going to give you Cartesian this way, and Cartesian that way, and Cartesian this way, fine. You probably don't even need to worry about it. But you always have torques, and the torques are usually what kill these things, not the forces. So I was probably talking to someone about ATI force sensors too. It's the same thing. Torques are usually nastier in mechanical systems than straight up Cartesian forces. Okay. Let's talk about something else that's very nice about these, and I suppose I shouldn't have taken that off. Let's look at a picture of one of these things. Actually, let's go back to the moments. Say I have a really tight space, and I just can't spare any bigger of a slide. Hint. Well, actually, let's look. So H is the height from the rail to the top of the head. And then let's look here. For height 8, this is 7.5 Newton meters, and then up to 20 is 80.7. So we're monotonically increasing in terms of the torque loads as we get bigger. Right? That makes more sense. Say I don't have room for the big one, but I need the torque capacity of the big one. So I'm going to buy the little one, and then I need to increase the torque capacity. What do you think I can do to increase the torque capacity? Any ideas? Somebody look at the Silver Falcon for inspiration. How many rods does the Silver Falcon have? 2. Do we have to have 2 just to constrain the motion here? No, we only need 1. But we could add a second one to give us additional torque carrying capabilities. Now let's look at this. If this is my rail, and this is my head, I have some torque limit here. Now if I put a second one on the same rail, will I have parallel issues? No, I will not. So what I can do is, say this is my load, I'll bolt it on top of both. So in this direction, I get much higher torque capacity. In this direction, I get much higher torque capacity, actually in all 3 torque directions. We get a little bit about roll, but not as much as we'd like. How do you think we increase the moment carrying capacity about the roll?
A second rail.
A second rail. So now, yes. Okay, so now let's put these, and now let's extend this over here. Okay? So now these two rails will give us much higher torque capacity in this direction. This is a very common configuration. Often you'll get rid of these ones right here, and you'll just have sort of two like this. And then what's the last thing we can do, not in terms of the number but just the type? We can extend it like this. So we can take one block and just make it longer. So when you're looking at Misumi, this is called the long block. And then if we cut it off here, it'd be the short block. And the reason why they have long and short is because it will give you more or less moment capacity for one single head. Okay? Now, as Annie said, we have parallel issues. If these are cockeyed, this thing is going to bind. Now, this is a very common configuration that people use, but you do have to be super careful about location and installation, because otherwise it'll bind and it won't work. So use dowel pins on the correct reference sides, and then if you're really doing it, we'll talk about sort of the order of operations in terms of the way that you tighten the screws really matters. And sometimes you have to do things to adjust for parallel issues along the way. So another one of the things this gives you, hopefully, see this right down here? I don't know, I'll read it to you in case you can't see it. Running parallelism of surface C against surface A, and running parallelism surfaces D against surface B. I don't know where page 497 is. Probably before page 498. But that basically is saying how straight is this shaft. So what they do is they'll put a little dial gauge on here and run it against a very smooth surface and just see how much the dial gauge bobs back and forth. And that's the parallelism. Now, I told you that most of the time people don't care where this rail is in this direction, right? I mean, if they did, they'd give us some type of datum for that. They do care where it is this way and what angle it's at. About half the time they don't care where this block is this way either in terms of affixing things to the block. As long as you're at the right angle with these two dowel pins, you're okay. Sometimes it really matters that you know where you are on this block. So in my dissertation robot I have a bunch of these and it really matters for me. So up here they add something extra, and this is why I picked this particular block. Write down S, E, L, B, and L. You may have to order this at some point. What are these? Middle holes. So these four are screw holes, and what are these? Those are dowel pin holes. So let's, if this is the block, these are the screw holes, and then I have one hole. Does this constrain enough? Okay, so now I have two holes. Is this a good idea? This is constrained, but is this a good idea? Have I talked about this yet? Ooh, delicious. Okay, this is kinematically constrained, right? Do you think this is easy to machine? I have one block with two holes and a second block with two holes. This is very difficult. You can do it, but it's going to be painful. So instead what I'll do is I'll replace this with a slot. Now it's a high precision slot, so the slot width is the same diameter as this hole. Okay? Now my second pin, say this is the other block up here. One pin's here, and say that's perfectly aligned, and then this second hole, the second pin can be wherever, and it won't be over constrained. It might be inaccurate, but it won't be over constrained. So this pin can move anyway, and mainly, what does the side of this hole set? Okay, let's back up for a sec. I'm going to use a book, and we'll give Ed some free advertising because it's Ed's book. Okay, so imagine this is something I want to put on this block. Okay, and I'm going to put two pins in here. The first pin constrains rotation. Okay? The second pin, if it were just two pins and two holes, would simply lock it in place. but I'm going to put a slot here instead. So if this is one pin, the other pin can be anywhere along this line, and it's fine. What happens if the other pin's up here? Then I'm at an angle. But the reason why I put the hole this way instead of this way is because I'm most interested, this fixes the point and the side of this hole fixes the angle. See that? This is super useful. I can't tell you the number of parts that I have this in my robots, like everywhere. This is what allows your robots to simply snap together on the first try. If you try to do 2 pins in 2 blocks, it ain't going to happen. But you need to make sure you have this slot aligned where you want it to be. Okay, let's try another one. Say I have this is off topic, okay? Say I have 2 circular plates that I want to align, and I care about the angle in between them. So I have a central hole, and if I put another second hole, then that's going to over-constrain it. Do I want the slot to go this way or this way? This one, okay? Okay, what if I want it to be along a 45-degree angle? This one or this one? So trick question. It's neither. It's radial. The answer is for circular plates like this, it's always a radial slot. So what this lets us do is we can bolt whatever is on the head of the linear slide, and we know precisely where it is with respect to this head. And sometimes that's extremely important. McMaster doesn't sell this, only Masumi, and not very many of the slides on Masumi have this. This is pretty special. That's why I gave you the part number. Are there questions thus far? Okay. Yes. Well, of course. Give me one sec, guys. Sorry, it's the notes are long and laborious. When I say grease nipple, please do not tell me what comes to mind. I'm sure it's terrible, and I'm sorry for putting that image in your head. But in all seriousness, there's something called a grease nipple. And let me show you what that looks like. You only find these on really big slides. I'm sorry, this is a terrible image. This is literally called a grease nipple. What do you think you use it for? Just to pour in lubricant. So basically what happens is, if you put a reservoir of oil and the balls keep dipping in the oil and taking the oil with them, and then that oil gets deposited along the length of this linear system, eventually you're going to lose all your oil, right? So if this is installed somewhere for 10 years, you have to go in and service it, so you're going to take a special little oil squeaker and put it on the grease nipple and insert lubrication. Don't apply loads to them. Don't touch them. If they're in your robot, make sure they have clearance. Never touch them. They break off really easily, and then your slide's dead. Let's talk about other ways of killing a slide. How else could I kill this slide? Not mechanically, in terms of I bend it or smack it. Okay, don't smack it. That's another thing. But how else can I kill this slide?
Just the dust or something that goes in and jams in the balls along the side.
Okay, and what might get in there to jam the balls? Dust? Anything? So I love these things, but I hate these things, because if you get anything in them, they're dead. If you get dust, if you get debris, God help you if you get a piece of metal in there, the slide's dead. The other thing is, if you smack it with a high impact, remember from ball bearings we talked about Brinelling? Basically, if you plastically deform any of the balls or the rails, then you hear the ka-kunk, 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 ka-kunk. Actually, good question. No one asked it, but I imagined you did. Say I smack it with a hammer. Something bends, and then I run it back and forth. How can I tell if I hurt the rail or if I hurt a ball? If I hurt the rail, I only have sort of weirdness at one point. If I hurt a ball, I'll have a cyclic ka-kunk, ka-kunk, ka-kunk. And then If it wasn't a preloaded one, say it was from McMaster, then you could replace accordingly once you know if you need to replace the head or the rail. Don't get dust in these things. So in your designs, you need to make sure that you put covers or something so that we don't get dust in them. They actually have these things, they're like accordions that kind of sit along here and cover the rail, so it moves back and forth. Imagine a pair of like really baggy jeans on here, only they're accordions, and they move back and forth. And then the next thing is seals. Remember how I gave some of you sealed bearings? They have seals on these too. And let me show them to you. You guys see this green thing? It's kind of shimmery. That thing right there. And you see how my thumb is able to deform it? That's a rubber seal. So that actually sits along the rail and takes up any clearance between the head and the rail to keep dust and contaminants from coming out. That doesn't mean you can't get dust in. It just means it's harder. Now, what does this add to the system that's bad? Friction. So in the haptic device that I built that had a prismatic radial degree of freedom, it had seals on it, and that was terrible in terms of friction, so I took them off. But then it made me really nervous in terms of dirt. So it's a trade-off. All right. We're making good time, actually. I know this is boring as hell, but this is really important. What's the main advantage of using, well, so because we're preloaded, what does that get rid of? Backlash and wiggle in various degrees of freedom. So this is a huge advantage in terms of using these ball bearings, linear ball bearings, is that they're preloaded so it get rid of backlash. But what's the main advantage that I've been trying to tell all of the teams who have asked me about it thus far? Why would I want to use one of these instead of, I don't know, 2 linear ball bushings over here? Simplicity. This is one part, literally. From Masumi, it comes in a box, you take it out, you screw it into your robot, and you're done. And it comes with locating planes and everything, and in this case, dowel pin holes to make your life easy. This way, you have to machine the block, you have to make sure it's parallel, you have to mount the rods. They give you nothing for free when you do linear ball bushings or when you do splines or any of this stuff. The linear guide / reciprocating linear ball bearing is simplicity at its best. Well, it's not simple, there's a lot going on inside that head, but it's abstracted from you, it's a black box. So I use them everywhere because it's just a single part.
What's expensive?
Huh?
What's expensive?
So on McMaster these are about $120, and then actually let me show you this. Believe it or not, this tiny little guy I think was like $80. This is real tiny. If $120 is expensive for you for building a robot, and I don't mean to be callous, you probably should not be building robots. Robots are expensive, and you have to think about expense as more than simply a dollar bill affixed to it. Your time, whether your bosses agree with you or not, is the most precious thing you have. By the time you get out of here with an advanced degree, you're really expensive. And it's not just your salary, it's healthcare and everything. So if it takes you 10 times as long to build something with linear bushings, then that's way the hell more expensive, even though the raw components are cheaper because you had to take the time to design it and install it. And also get things machined. Machining is really expensive, even more expensive than your time, because now it's your time plus 2 other guys' time. So, and I realize you guys are paying for this out of your own student budgets, and half of you are probably eating ramen anyway, as I was in your position. But if you're doing this for a research or a company and they balk at $120 for a linear slide, you need to go find a different employer. Robots are expensive. If you mass produce them, that's a different story. But if you were to take the automobile, the only reason it's cheap is because they literally sell like millions of them. Okay? But if you were to build in an R&D lab a brand new automobile, say my lab decided we're gonna make an automobile, it'd be over $1 million easily. The only reason why automobiles are cheap is because they like have robots that assemble them, and they make them by the millions. So building stuff is inherently expensive. So going back to your comment that these are expensive, compared to ramen noodle soup, it's very expensive. But for the time that for what they do and the time they save, I would pay 10 times the cost. They save so much time. And you probably won't be able to believe me until you try the other ways. The other ways are really painful. Okay, so we've talked about how to constrain motion. Now let's talk about how to drive motion. So remember back from lab 1? Rack and pinion. So this is like, the dumbest way possible to do it. I don't mean it's bad, I just mean there are 2 gears and that's it. And that's pretty sweet. And remember, this is apart from how we guide it. Assume we're using one or more of these ways. So it's going in a straight line, now we just want to power it. So we can do rack and pinion. Okay. What's the disadvantage of that? Backlash. What is the advantage of it for those teams of whom I've been trying to disabuse more complicated methods? Simplicity. It's so simple. And you can laser cut it. Rack and pinion is super simple. In terms of loading, it's really nice on the motors. Remember, belts and cables have pretty high internal tensions that try to kill the shafts of your motors. So if you were to say for a final project in the class that you loved so much, want to do a linear system and power it with a servo, then a rack and pinion would do a great job for that because it's not loading the servo shaft as much as, say, belts or cables. What are other ways analogous to rack and pinions that you can imagine as a transmission for powering the linear motion? We can do friction drive. If I were to draw the friction drive and draw the rack and pinion, what would be the difference? Teeth, or the lack thereof. Okay, so all you have in a linear friction drive is something flat, or maybe it's not flat, something constrained in linear motion, and then something round and squishy. So it could be a rollerblade wheel. It doesn't actually matter if this is what shape this is, as long as you don't do something bad to your track roller. Does this have to be a point contact? Okay.
It won't be.
Yeah, it won't be. Well, it could be, but we're not going to have it be. Say we made this a circle, and say we made this cross section like that, we could do a point contact right there, but it doesn't have to be. Unlike that friction differential where we had to mathematically have a point contact, we can have this be a line contact. Okay? We could have this be flat, and then we could have this be rectangular, and that would be fine. And if we're using rubber, where we break some fundamental laws of friction and the surface area counts, we'd have higher traction. Okay, we could also do a cable drive. Remember lab 3? Were I to take lab 3 and draw it on this board, express in one very short sentence how I would draw it. Think of fruit roll-ups. Were I to take a fruit roll-up and analogize it to lab 3, in that it is circular, and I wanted to eat said fruit roll-up, what would I first do? I would unroll said roll-up. Okay, so this is lab 3, where, okay, and now we're going to unroll it. There's no magic here. That's the whole thing. Just remember, fruit roll-up. Lab 3, linear cable system. There's nothing different. And still we need some way of tensioning this. So maybe you'll have this go around a little bend. And then say we crimp it. You remember the trick we did with the Delrin plate and the screw moving backwards? So that's a linear cable drive. And I actually have one right here that I'm going to briefly put up here for you. Okay, everyone see? What's this using? What type of linear guide? Linear guide. This was the reciprocating ball bearing one. Okay, and then underneath, whoa, I can see that, but you can't. Do you see the capstan? Okay, Alice, can you hold this for me, please? Sorry. This is acrylic, so it's shiny. See how it's rotating the motor? So it's just a cable and you're free to come after class. And that's the whole thing. Okay? Cool. Thank you. Sorry, all tangled up. Okay. So we got rack and pinion, we got friction drives, we got cable. Now I'm going to give you a second cable. I didn't bring it up here because I'm lazy. This is from my haptic device. Can everyone see this? So this is a linear, this is the rail of the reciprocating ball bearing. This is the head, and this is the cable loop. These little indentations are from rerouting pulleys. So I'm terminating on the head, on a block on top of the head here, and I'm tugging from different directions, and the way I can do that is I'm redirecting up here, okay? So this is a cable drive. Does everyone see how this works? Imagine I take my book, and I put one string here, and I put one string here, and then I just yank them back and forth. Now the reason why I'm telling you this is slightly different is this doesn't have to be a cable. This could be a belt. It could be a push-pull. It could be whatever you want. The idea is you get on either side of the slide and pull it back and forth. In this case, it happens to be a cable. Everyone see how this works? This is really common to do with belts. Not all this crazy rerouting stuff, but it's really common to do with belts. Okay, so we've basically left out the most common linear method of driving. So someone give me a shout out for what you think it might be. The screw! Usually it's called a power screw for power transmission. These screws are not the same as the nut and bolt type screws you're doing to hold your robots together. These have a different type of thread. Often the thread is Acme thread. Acme also makes great anvils. And if you get real crazy, you get proprietary shapes, and they won't give you the shape of it. And they'll do that to decrease backlash. But typically it's something like Acme thread. Right-handed and left-handed. Man, that was close. Put your thumb in the direction of the screw, wrap your fingers around. If they follow the helix, it's right-handed. If not, it's left-handed, assuming you use your right hand. All right. So I'm going to show you something awesome. Rob, can you please train on the screen and then come assist me? Okay. Go ahead and turn it on. Oh. 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 Okay, so this is a power screw. Remember, power doesn't have to mean huge. It just means we're using it for actuation. So all I'm doing, this is what actually constrains the linear motion, and then the screw is what moves it back and forth. Okay? Now, this screw is although the threads are different and the materials are different, this is pretty much like What type of contact is this? Sliding or rolling? Sliding, which means we have what? And backlash. Because it's a sliding contact, we have friction and backlash. This little nut, can you zoom in, Rob? This little nut, oh God. Okay, this little nut is made out of plastic to decrease the friction. And then you see this little, it's black on both sides, and then there's this weird silver thing in the middle. That's a spring. This is an anti-backlash nut, where basically they're using a spring to preload and get rid of that backlash. You don't have to have that. Let me show you what it looks like when you don't have that. So this is literally just a piece of screw rod and a nut, and it's just a piece of plastic. See? But if I had a spring in the middle that took out the backlash, that'd be called an anti-backlash nut. Okay, now the cool things about screws is you get them huge and you get them tiny. So I'm now going to show you a bunch of huge and tiny, and you get the idea. What do you want to see first, huge or tiny?
Huge.
Okay, huge was louder, which makes sense. Has anyone heard of the company Fergelli? Fergelli, look them up. They make huge and they make tiny. They also make in between. Basically, it's linear servos. Okay. Okay, and can you record me? Oh, shit. And can you zoom out a little bit? Or should I move back? Okay, so you can see this is gigantic. This is big and honking. A friend of mine got this for counterbalancing a robot. It was going to stretch a spring. Okay? So this is big. They come bigger, but this is pretty big. Okay. Now I'm not going to power it. Now this is sort of medium. Okay? And this is tiny. Muy pequeño. See, it's cute. I named this one Fred. Its brother Bartholomew died. Okay, so I'm going to lower the voltage and we'll show you this one. Now, when you're going to buy these, they might be on different parts of the website. I think one of them is like Fergelli Automotive. Maybe, I don't know. Okay. Can you come zoom in? See? Now these guys are cool. They have a potentiometer in them so that you can sense where you are. And they have little built-in limit switches such that you can't drive too far. So do you notice how it stopped? That was not me being really quick on the trigger. They have it in so when it hits the limit switch, it automatically shuts off power. So for your entertainment, I have killed one of these and ripped out its guts. And then later we'll bury it on the quad. Let me show you what this looks like. This was one of the medium-sized ones. And let's make some room. Okay. Okay, Rob. So there are several discrete parts to this. If we were to stick this back on, this looks like it used to look, right? Oh God. Can you see? Can you move, Rob? Can you see how this sort of looked like what it used to look like? Okay. So the first thing I did was I took this off so we could figure out how it's moving. So all this is a power screw, and then this is just some wiring. This is one limit switch, and then over here is another limit switch. And then, Rob, can you zoom in on this, please? Okay. So this is the nut. Tell me something obvious about it. Okay, it's plastic. Low friction. What else? It's what?
Was that flange to hit the limit switches?
It is flanged. It can use that to hit limit switches. What else can the flange do? Flange keeps it from rotating. Let's look inside here. Look into the abyss, please. Can you zoom out? The flange fits in here. That keeps it from rotating. So now what I'm going to do is prove to you once and for all that the screws don't work if you don't hold the nut. And as funny, I'm also going to teach a good lesson about linear systems. Why do you think I have these? They lube the shit out of these things, and it's nasty stuff. Can you? Creature from the Blue Lagoon, can you go back? That. It's all over this thing. So, buyer beware if you take these apart. It's really nasty. Okay. So, let me plug this in. And I need Ellis as a Von Deer, please. Because you're sitting too close. Don't have time to run away. Okay, so I'll give you the power. Okay. Oh, shit. Okay, don't press anything yet, or it'll eat my hand. Okay, Rob, let's do some nice zooming in. A little too much. Okay, so this is the motor. This motor spins this little pinion here. What's this? It's not an idler, actually. It's a compound gear. Okay, so motor to pinion, compound gear, another gear to the screw. Okay, now Rob, zoom out enough that we can see the little this. Okay, so what I'm going to do is I'm going to hold it up and go ahead, Alice. Oh shit. Give me a sec. Don't do anything. Go ahead. And, okay. What's happening? Keep going. Why isn't it moving forward? Just spinning. Some of you, I know, and it's okay, we don't have to name names. I know you didn't believe me that cable tensioner would actually move back and forth, because until you kept the nut from rotating, it just spun in place. It's the same thing. Do it again. Nothing's happening. Okay, now quit for a sec. Now, I'm going to, with my hand, keep it from rotating, and please don't ram this. Go ahead. Look at that. And go the other way. Okay. Now, I want you to go that way, and in my hand, I'm going to take this limit switch. So mechanically, when we hit the limit switch, this is what happens. Go ahead. You still pressing? No, keep pressing. Alice has the juice on, but I've hit the limit switch and it's not moving. Okay, go ahead. Okay. Now go the other way and I'll hit the other limit switch. Okay? The limit switches are hardwired so it can't kill itself. Alright. Now, how does this thing sense where it is? I said there's a potentiometer, right? Zoom in here, Rob. Oh. Back. Alright. This little plastic gear goes up to this part. And now we have a gear train. What's the blue thing? Not only is it a pot, it is a multi-turn pot. And you see we've got a bunch of gears here that spin the potentiometer. And if any of you are interested, come by later. This one here, does anyone know what that's called? Imagine putting it on your head as a hat. Crown gear. It's a crown gear. Okay? So to review, we go motor, zoom out, Rob. Motor, compound gear train, welcome to Sony. Lead screw, can you toggle please? Apparently I have low stamina. Oh God!
Sorry.
Oh, now I have no fingers.
I thought you meant me. Sorry.
Okay. We keep this from rotating, we have 2 limit switches, and then we come up here to a potentiometer for closed loop feedback. Okay, we're good. I'm going to power this thing down before I lose a knuckle.
Sorry.
It's okay. No problem. So these are really common, and they come big, and they come tiny, and they come in between. Because Rob has the camera, I'm going to introduce you to some other concepts real quick. We talked about the anti-backlash nut. Remember going back to lab 1? What's this called? I'm driving the output? What's driving the input? Okay. This exists in the screw world as well. So let me come over here. So just to show you what I got right here, I have something blurry attached to something else blurry. It's a very nebulous affair. Okay, so we got a screw, nut, screw, and then this is a little laser cut gears, and this is a little gear motor. This was something I was testing out. So this that is back driving a screw. Okay? It's getting pissed at me. It's probably not the screw, but at any rate. Okay? Not all screws back drive. Do you guys think your M3s or your M4s back drive? No. That's why they're good screws. But these aren't meant to be like fastener screws. These are meant to be transmission screws. So
You can do like compliance system. If it's back drivable, then compliance would be easier. Do you think? Like mechanical compliance?
I'm not quite sure what you mean. Let's come to that at the end of the lecture. We've got a couple more things to go over for screws. So power screws are a giant squirrel hole. So I'm not going to tell you everything that exists about them, A, because I don't know it, and B, because it would take until next week. I'm just going to tell you the bare minimums, okay? Let's start out with how we might want to put a screw in a system. You just saw one way. Let's do another way. Remember the two rods way? I have two rods. That constrains the motion. But I'd like to put in a screw. Should I do left or right? Thank you. The non-option. I actually want to put the screw down the middle. Why? If one of these is made of screw, it's going to cock constantly. It's going to get jammed because one side will be really loaded and the other side won't be. You always want to put the screw dead middle with the two guide rods on either side. Putting this as just the left or just the right will fail fairly reliably. That doesn't mean that many people don't start out doing it, but it just means it's terrible. So just to show you, this is a super ridiculously common mechanism. This is just a clamp from the shop. Okay, so we have one guide rod, two guide rods, and a screw in the middle. And when I rotate this, it moves. Okay? So this is one way you might use a screw. Or we could say this is the linear guide. We could put a screw up here attached to the head and just put some bearings here and house them. That would work too. Okay. So let's talk about something, and I'm just going to have Rob film the book because I'm too lazy to draw it. There's some terms that are very important in screw theory. And just so you know, screw theory actually is Bernie Roth territory. I used it improperly. Screws are also a mathematical way of talking about rigid body displacements, so don't get confused. Okay. And let's do right here. Okay. So these are two screws. And can you zoom in, please? Out a little bit. Okay. So this is a single thread. Believe it or not, you can also have multi-thread screws where you have multiple helices. Imagine I take one screw and then I start wrapping more helices around it. Like, what's a common double helix? DNA. So DNA would be how many starts for a screw, or how many threads for a screw? 2. Okay? So this is like DNA. Now, the linear distance between peaks of the screw thread is called the pitch. In this case, it's also called the lead. On the multi-thread screw, it's still, the pitch is the distance between adjacent threads, and the lead is the distance that the screw travels in one revolution of the screw. So let me get the screw back out. Zoom out. Okay. Say when I twist this one revolution, that's half and then another. However far this moved, that is the lead. That doesn't mean it's the same thing as the pitch. In this case, can you try to get the very tip? You may not be able to get the very tip. Yeah, you can't. Do you see how when I spin this, there are multiple little shiny spots on the end? Each one of those little shiny spots is the start of a screw thread. So this is a multi-thread screw. So the lead is different from the pitch. Very important for the math to work out. Okay? Now I'm going to draw some quick stuff. We will get to that in just one sec. Okay, so let's draw some stuff. This is the lead. Lambda is the lead angle in degrees typically. And then this distance here is pi dm, where dm is the mean diameter of the screw. It comes to about halfway up to the middle of the tooth. Okay? And then let me give you some other stuff. This is, you may not, I mean, this may just be like totally like, whoo, but that's because we're doing it really super quickly. Don't talk about gear ratios with screws. It doesn't really make any sense. Tau is force times L over 2 pi, and then it's normally called nu. Okay, L is what? I just told you. Lead. F is axial force on the screw. Tau is torque applied to the screw. Pi is obvious. Nu is efficiency. And Rob, can you please take your post back there? Nu is efficiency. Alright, so it's between what and what? Numbers? 0 and 1. Okay. Now lots of things tell you about the efficiency. I'm going to show you another graph. And again, the math goes on and on. I don't expect you to get all of it. I just want you to get the sort of general trends. Alright, this is a graph. This is the lead angle. This horizontal axis is the lead angle. So here's 0 degrees, and here's 90 degrees. Okay? This is the efficiency. This is 0%. This is 100%. And these different curves are for different coefficients of friction between the screw and the nut. So for what angle are we maximally efficient across all frictions? About 45. Now, just as a general rule of thumb, screws are back drivable if you're above 50% efficiency. It's a very rough rule of thumb. Please don't count on that. Just try back driving it. But as a usual rule of thumb in the industry, above 50% is back drivable, and if you want to guarantee it's not back drivable, usually you want below 35%. Another term for not back drivable in screws is self-locking. A self-locking screw is one that resting under its normal loads will not drive backwards. So you want to be here and below for self-locking, here or above for back drivable. God damn it. Be a lot better if Sonic the Hedgehog ran across. Anyway, so we'd like around a 45-degree lead angle, or sorry, helix angle, lambda. Now let me tell you some other stuff. I know this seems like, hey, thanks for the random information, but let's go over a few more things real quick. Okay, so lead is equal to pitch times what? Times the number of threads. Okay, so remember, if I do one helix, this is pitch and this is lead. And now if I do 2, then I have to redraw, and this is pitch, and this is lead. So in this case, lead would be equal for 2 threads to 2 times pitch.
So assuming they're equally spaced.
Yeah, they should be. So what this tells us, let's put together something practical. For the same size screw, the same diameter, and the same pitch in terms of the threads, if we add another thread, L goes up. What happens to lambda? Lambda goes up. And then, going back to our nice little graph, say originally we were down here on our curve. What happens when lambda goes up? The efficiency goes up. So one of the reasons why you see multi-threaded screws is because people want higher efficiency, so that they either aren't wasting all the energy or they get a back drivable screw. So if you really want a back drivable screw, you need a higher efficiency screw, and for a given diameter and pitch of screw, the easiest way to get higher efficiency is to add on number of threads. So I believe this guy here, Rob, this guy here has 16 starts, 16 threads, and it's like butter. So actually, let me come over here. I'm not sure how much you guys have time you've spent twirling screws, but I've done it quite a bit. So, okay, did you see that? Do you know how ridiculous that is? Look how far that's traveling. That's why it has 16 threads. It's a super high lead. Remember, another way of thinking about lead is for one revolution, and actually let's try it. For one revolution, so that's half and then 1, it's the linear distance back and forth that it travels. So the higher the number starts, the higher the lead. What's another reason why you might want a high lead on a screw? Say you have a motor. Same motor, 2 different screws, and you have a given no-load speed for your motor, but you want the screw to be traveling real fast back and forth. So what's a way to get higher velocity? To increase the lead. The lead is the axial distance it goes per revolution. If their theta dot is capped, then we need to increase the lead for it to go faster in terms of linear velocity. Okay, now, just because you have a finely pitched screw, in terms of the threads are close together, doesn't mean it's necessarily accurate. So if you're using these things for positioning, what you need to look at is the lead accuracy. Okay? That means basically, if this is the screw, and I know for one revolution, I know what the lead should be. So I should go from here to here. Where am I actually? This is plus delta what? That's the lead accuracy. And this is important because if you have something where, it can be anywhere along there, it's fine. Or if you have a medical robot that it has to be right there, you need high lead accuracy. And so you need to make sure to read that specification for the screw.
Is that correlated with number of threads or number of starts?
I have no clue. In terms of efficiency, there are many different equations for backing out efficiency. If you're buying it from a reputable person, i.e. not McMaster, then they'll tell you the efficiency of the screw. And if they don't, email them and ask them for it. They have all of the data, guaranteed. So rather than you going through, if you don't get the efficiency from them, you have to make a bunch of assumptions about friction between the nut and the screw. Those assumptions are most likely incorrect. So just ask the manufacturer what the efficiency of the screw is. Okay. So we said we could get rid of the or at least mitigate the backlash with the spring loading, multi-threading. Another term for number of threads is starts, or number of starts. Now, we've got this screw, or Here, let me take the screw. Rob, can you get the screw, please? So I take this screw and I put bearings on it, and then I push this way on the nut. What failure mode may happen to this screw, like this? Huh? I might shear the teeth on the nut, yep. Say I give you some ridiculous space age technology like Tang. Everyone knows Tang was made for space, right? Like one person got that, okay. If I push on this and I have an amazing indestructible unobtainium and it doesn't break, so you're right. With plastic it probably will shear the teeth, but it's unobtainium now and that won't happen. Now it's the failure mode. It's going to buckle. If I push this way and I'm constrained this way, we have a compressive load for this part of the rod. So a pretty common failure mode for screws is buckling. And if you don't believe me, after class, take this and kind of wiggle with it, and you can actually see the screw like starting to bend either way as if it's about to buckle. Please don't break it, but you can at least play with it. Okay, so if you get really nice screws, they'll have anti-backlash nuts. They'll probably have some type of proprietary, better than Acme thread for reducing backlash. And also, they'll have some type of anti-friction coating. So it won't just be like a steel screw, it'll be a steel screw plus, I don't know, Teflon coating or some proprietary coating. Screws, unless you buy them from Asumi, have to be machined in terms of the ends, right? Like I bought this block of screw, but I need to put a bearing here and a bearing here. Don't do it yourself. Send it to a machine shop. When you clamp this in the lathe, the odds are you're going to crush all the teeth, and then you're screwed. So when you buy this, send it to your local lathe shop, let them machine it. Do keep in mind, if you're not buying it from Asumi, sells lead screws with nice ends for doing this stuff, plug and play, but I've had to make plenty of screws. Send it out, because otherwise you'll crush the teeth. Okay, now let's talk about the best type of screw you could get. What type of contact is this again? Between the nut and the... This is a sliding contact between the screw and the nut. And what would we ideally like? Rolling. Now we've seen rolling linear bushings and rolling linear bearings. So what do you think, based on that, would be the corollary for a screw? Screws plus a ball. Screw plus balls, sorry. So it's called a ball screw. I don't have one here. I have a bunch of them in my robot. Yes, I know. Hee hee hee. So it's called a ball screw. And instead of an Acme thread, which looks kind of like this, like this, what do you think is the shape of the screw, of the threads on this? Round, for little balls. Okay, so I'm going to show you what that looks like. Now, for those of you who get super excited about stuff like this, ball screws are freaking amazing.
Your ocean parts and used some research and
And if you haven't had your fill of if you haven't had your fill of infomercials, go to YouTube and type in these various things and enjoy the infomercials. Okay. So inside it are balls, and this channel is where the balls come over. See? Remarkably, they're not that expensive. And they're super common.
Is there a reason for them to be more than just one thread?
Distribute the load. So these are like the gold standard if you're going to use a screw in a high precision robot. Somebody tell me why this is higher precision.
Swedish.
Well, yes. Because it's Swedish was a given. Beyond its nation of origin. You can preload the balls. Okay, and so that gets rid of the backlash. Now Misumi sells ball screws. Misumi sells all of the components for a linear system. They sell the linear guide reciprocating ball bearings. They sell the bearing mounts for the screw. They sell the ball screw. They sell the nut for the ball screw. They sell the things that then mount. They sell it all. Okay. They also sell completed units. Don't build your own linear systems if you don't have to. For a class where I'm forcing you to, that's how you should do it. If you're doing research or for a company, don't build them, just buy them, okay? So if somebody says, hey, I need XYZ, you go to Misumi, you buy the LX45, this might be something different like 26 or 30 or whatever, it's the LX series, and it comes with the linear guides to give it linear motion, plus a ball screw to power it, some of them plus a motor or at least a motor mount. It's the whole deal. Some of them even can include the motion controllers. And when you buy it from Misumi, it gives you some specifications in terms of backlash, and then they actually measure them. So they measure each one, and when they send it to you, they tell you what the backlash is. So I have an LX45, and it's stout enough that I can literally sit on it and it will drive me back. I'm not joking. I won't break it. I could jump on it and it wouldn't break. It'll drive me back and forth about this speed. It's only about that big around. I can get them up to this long. Includes everything except just a place I plug in my motor. And it comes with an inspection certificate, and I think mine had 6 microns of backlash. And it's back drivable, so I can push it back and forth with ease. So let's talk about that back drivability. Ball screws are way higher efficiency than lead screws on average. I think all of Misumi's ball screws typically, I think, and please don't quote me even though we're recording this and I'm telling you, so you could quote me easily. Ball screws are typically greater than or equal to 92% efficiency because of that rolling contact. All of Misumi's are above 92% efficient, which means what? They're easily back drivable. Assuming you didn't do something crazy, but yeah. Okay, a couple more things.
Hey, Ruben?
Yeah.
So in the screws that have like say 16 different helixes,
Uh-huh.
does the nut that go on have to have exactly those 16, or can it have like 8 out of those or something like that?
I mean, an excellent question. I don't know. I'm pretty certain it has to be exactly matched. And you're going to buy the nut. Like, please don't try to make your own nut. Just don't 3D print it, just buy it. Yep.
Since you were talking about back drivability, is the main advantage of that just being able to back drive it yourself without the motors or anything?
No. So, I mean, A, it's efficiency. So say it was a battery pack, then your battery won't die as quickly. B is that it's much more precise in terms of you have much less backlash because it's preloaded rolling contact versus sliding, which inherently has gap in it. And typically, this is just me pulling stuff from bad places, is that because they're so expensive for like the integrated units with the ball screws, they're also higher precision typically. So that accuracy, that lead accuracy, is often better. Okay, another linear actuator is a pneumatic or hydraulic cylinder. Can you zoom in, Rob? Okay, so that's cool. But this does not resist rotation. Okay, so I can rotate this back and forth. So if you wanted to put this in your robot and put your little gripper on it like this, then your gripper would be changing. So just linear motion, but you still have to constrain rotation if you need to constrain rotation.
But even driving it is linear, so you can't drive it with a motor.
You could. Imagine that I put 2 rollerblade wheels like this. Oh god. I could smush it in between. Let me draw it. I could take, if this is the rod, I could take 1 wheel, 2 wheels, compress them together like this, and then when I rotate, it'll go back and forth. Why do I have 2 instead of 1? because if I only use one, it's going to bend the shaft that way and break it. So, but you are right in that it's linear to linear, not rotary to linear.
I mean, if you're doing that much, then you might as well just drive. Like, why do you want to drive this, which drives something else?
Because I can put this anywhere. I can take this all the way to the end of my robot, and I don't have to. If I was to do this with cables, I'd have to have reroute cables, pulleys everywhere, whereas this can go wherever. Also, this has what? Inline compliance, if you liked doing that type of thing. Okay, another common place where you'll see linear bearing or linear motion is microscope slides, because you have some type of nasty bacterium that you want to move back and forth and look at it. And so I'm going to show you one of those, and then I'm going to have you tell me what some of the components are now that we've talked about all of them. Don't worry, we're almost done. Okay, so this is my little microscope slide. So I rotate this. This is a micrometer input in that I can read off the scales like a micrometer. And then these are the two linear ball bearings. Now let me zoom in. Can you see the balls there? See that shiny thing? Those are the balls. So I have two of them. What do I have to be careful of when I have two of them? The alignment to make sure they're parallel. Now, something unique to microscope slides is this. Spring-loaded. This is not a screw. Oh, okay. This is a screw, but this is not rigidly attached to it. There are springs that hold it against this surface here. This is a little hemispherical ball that rotates so that you have zero backlash. So one way of getting rid of backlash is just spring loading the hell out of it. Okay? No backlash, no special nut here. It's spring loaded, and this doesn't have anything to do with linear motion, but it's really cool, so I'm going to show it to you anyway. Let's zoom in. Can you guys see at all the there we go. See that? What's that? Give you a hint. Spring. It's a spring. There are two of them. What is this little guy down here? It's just a rod. Okay, now put the two together. Now, what is this? It's a rod spring. Genetic hybrid. Mamba pig. This is a spring with a rod in the middle of it. The funny thing is, he got a Nobel Prize for that creation. The spring is on a rod so that it doesn't fly off and so that it's linear, okay? So remember how I was telling you in the springs lecture how often you'll put some type of a rod core to the springs? So this is an example. And let's zoom in here. You see the ball tip? That can rotate. So microscope slides are almost always linear, although they do have some revolute ones.
Oh, so it's just pushing them?
It's just pushing it. So yeah, this is just free to go wherever on the spring. All this is doing is pushing on it, okay? Now if you had something that overcame that force, it wouldn't be accurate, but as long as you're within that force, you're good. Now if you want super ridiculously nice linear slides, you want to buy microscope positioning stages. They are crazy. I got some. There's a place in Redwood City that sells on eBay used. Basically, they cannibalize companies when they die in the Bay Area. So they swoop in and buy all their $100,000 slides and sell them for $2,000. So I got a set of them for a robot by Newport, like $2,000 each, and they used to be like $20,000 each. They're ridiculous. Super nice linear guides, reciprocating ball bearings. They had tachometers for velocity sensing. They had a glass scale sinusoidal encoder that had resolution down to 0.1 micron. I mean, it's a microscope, right? So if you move a little bit, your microscope goes flying by on the bacterium. So it's like super high resolution. Anyway, also typically, the microscopes are not like wee little, junior high microscopes. They're like gigantic electron microscope or huge optical ones. So they can take really high loads. Anyway, Let me check to make sure that's the end of the torture for you guys. Are there any questions about today's lecture and not about the final project, which I know is on the tip of your brain?
So about this anti-backlash nut, how does a spring? That's a spring too, right? How does that work?
My guess is it twists the nut. I'm not sure. Some of them are axial and some of them are torsional. So the answer is I don't know. So go to just Google lead screw anti-backlash. Also, you could Google Nook Industries. Nook Industries sells a lot of these, and they have some really good tutorials on screws. Okay. But it's either an axial or torsional spring, and it has something to do with twisting, basically twisting or pushing that gap away. Other questions about today's lecture? Linear motion? Let me save you guys the trouble of going through weeks of design and coming to the same conclusion. For your final project, if you're doing prismatic, and note that you do not have to do prismatic, you probably want one of those single piece reciprocating ball bearings that I raved about. They're about $120 on McMaster. They're like 7 pages on McMaster. You want the second to last page. You probably want one that's about 12 millimeters base for the rail. You'll see they sell ones that are like 7 millimeters and that the loads are way higher than you need. Actually, let me just go there real quick. This is officially the end of lecture. Anyone who wants to go can go without retribution. But for any of you who want to talk about the project, I'll do that. So, linear guide. Okay, so you go to McMaster, and we're going to keep recording, Rob, for those of us who were not here. Okay, linear guides. See, this looks familiar. Up here, see how there are like a bunch of pages? Go to page 1099. Okay, I'm looking for the muy pequeños. Down here, this is rail width. They've got all the way down to 5 millimeters. You probably see dynamic load capacity 151. I don't know what the hell that means because they don't say XYZ or moments. It's just sort of a load. But the reason why you want a wider one, even though there's no way you'll need 748 pounds in any given direction, is when you bolt things down, to keep them flat, you need some width. Imagine this was super tiny and it was kind of like a razor's edge, and I wanted to bolt that perfectly at 90 degrees. Would this work? No. So take the razor's edge and make it bigger, and make it bigger. The bigger this base is, the easier it is to bolt flat to your robot. So even though the 12 millimeter one has 748 pounds, which is way more than your robot needs, 12 millimeters is starting to be the scale of things that will bolt easily to laser cut pieces of wood. 5 millimeters will bolt terribly. Don't do that.
12 is wide enough?
12 is wide enough, yeah. That's just based on my experience. So, you all are free to do whatever you want. If it were me and I was a student in your position, as I was years ago, just buy one of these. It's like $120. Y'all can't keep the robots assembled anyway because I need your fidgets. There are like 3 of you per team, so no one person's getting it unless they buy out everyone, including me. So basically one team member needs to say, I would like a linear guide for the future, and buy one. And then it will save you lots of time from doing, I've seen lots of 2-pole designs with linear bushings, but you can't laser cut the ends to be perfectly parallel very easily at all. I've seen designs with ball bearings like the one I built. I felt bad after showing it to you. It's cool as like a standalone demo, but then bolting that to the robot is hell. So anyway, yeah. Now, are there any, one last thing. Who has not received their flexible coupler? And I don't mean the second flexible coupler, I mean just the first.
Yeah.
I gave it to Camilo. You're on Camilo's team, right? Annie, you were there yesterday, right? With Camilo? I gave it to Camilo.
Okay.
If you didn't get it, come and let me know. Don't take one, just let me know.
Does this go 6 to 8?
5 to 8.
5 to 8.
Is that for the stepper?
5 to 8 for the stepper. Now, let's go over the email real quick, and again, you're all free to leave. It would behoove you to have one team member present at least. I sent out an email right before class. Let's just talk about it real quick. First thing is, I've decided to give you all a second coupler. Some of you would like to use a coupler between your DC gear motor and the shaft. I've made it fit. It'll be here on Monday. I've ordered all of the 80/20 that you need. I will give 80/20 to any team, regardless of whether it's chess robot or research robot. I have enough for everyone. You have the 25-2525. That means on a square, it's 25 millimeters. I've given you right angle brackets. I've given you end caps so you don't cut your fingers off. And a couple other assorted things. They're in the email. You have CAD for all of them but the nut. I'm trying to locate the CAD for the nut. Go to the website, download it. Now you can do precise CAD with your 80/20, okay? The servos. I, for the life of me, could not find what type of screw they use in the servos to hold the horn.
I think in the data sheet you gave, there is a spec for it.
Yes, there is.
The M2.6
by 0.45. Yeah, it's incorrect.
Really?
Yeah, that's for the metal gear servo, and we have the nylon gear one. And they kept telling me that, but I measured it. It's like a 0.9 millimeter pitch.
It's got a really wide pitch.
Yeah, it's actually 0.9 millimeter pitch, and the diameter is 2.5, and they don't exist. I think it's like a special screw for these things.
Like,
So,
I think if you buy a bag of those gear heads,
Yep.
they sell, it
Yep.
comes with like a
it does. But do you know the reason why that won't work? Not long enough. So remember, I'm not allowing anyone to use the stock horns. So, like, if this is the horn, and then the horn was something like this, this is super thin. So they gave you an 8 millimeter screw. But now what we're going to do is we're going to laser cut a big old fat adapter. Okay? Like that. So now we need a much greater length. So that's why we need another screw. So what I did, it turns out the screw diameter is 2.5 millimeters. Does that ring a bell for anyone? For anything cool? 2.5 millimeters. I'm looking for something practical. Think about other screws we've used. This is the tap drill size for an M3. So what I did was I took a 2.5 millimeter drill and drilled out the center of that screw hole. Then I tapped it for an M3, and now we can use metric and everyone's happy. Don't do that yourself. I almost ruined a servo. Let me do it for you. But all of your servos in your CAD use M3 screws. Assume that you can go measure the servo and assume you can go to that same depth, and now choose the screw for whatever horn you're doing. M3. Okay? We're almost done. Starter code. Turns out it's painful with the fidgets and everything. So I'm doing that pain on your behalf. So I'll release it probably tomorrow night. Is anyone here like dying because they don't have starter code yet? Raise your withered dying hand if you're dying. No, looks like everyone's still working on the mechanics. So there are some tricks, like fidgets forgot to do some things that mean you can't have multiple instances of the header. At any rate, we're debugging it. I'll release it tomorrow night. Before you go, I've got ball bearings for you. 1 bag per team. Take a Ziploc. Take 4 of these. They're 8 per that, so that gives you 32 bearings per team. I really don't think you'll need more than 32 bearings. Go ahead as you walk out. One per team, 4 bearings in a Ziploc bag. Don't lose them. I don't have backups.
What about the, so there's like a link that'll do the QP installation essentially?
I'll send that out. Yeah. Okay, we're done, Rob.